Hi, can you guys hear me?
Yeah, it seems like your audio is good.
All right. So I wasn't here last time we met, so I'll be starting with the session today. Welcome to session 11. We'll be covering some basic um concepts in number theory and uh basically concepts that are relevant to the AMCA. Number theory does show up in the AMCA and is crucial to understanding and solving a lot of different problems, mainly in algebra, because a lot of the times in AMCA and a lot of other math competitions, algebra and number theory kind of go hand in hand. So number theory is a very important thing to understand and learn because it's definitely going to be useful and it's going to show up in a lot of different problems in the future. So to start with some basic number theory, we'll go over the concepts of like a prime number, right? So, what is a prime number? Basically, a prime number is any number. So number n. Oh, yeah. So a number n that's greater than one, and basically, the a prime number is a number that its only divisors are one and itself, basically. So if you think about it, two is a prime number because the only divisors are one and two. Three is a prime number because its only divisors are one and three. And then also, I think it's important to clarify what I mean by divisors. Divisors are basically numbers that are perfectly so basically, right, like if I say that 2 is a divisor of 4, that means that if I divide this divisor by the number, I'll get something with remainder 0, right? So it perfectly divides the number. So again, like an example of a divisor of 6 would be 3, because if I divide 6 by 3, I get 2, which doesn't leave a remainder, right? Now if I said 5, 5 is not a divisor of 6 because 5 doesn't divide 6. If you divide 6 divided by 5, you get a remainder of 1, right? So um like that's exactly the point I'm trying to make here. So divisor is basically um, a number that leaves no remainder, if that makes any sense to you guys. Or I should say when divided by the larger number, just to make it much clearer. Right, so the only divisors of prime numbers are itself and 1. So, for example, 67 would be a prime number because its only divisors are 1 and 67. But would say, for example, 4 be a prime number? No, right? Because uh, 4's divisors are 1, 2, and 4. So naturally, its only divisors are not just itself and 1, right? There's 2. Um, Also, here's an important note to make. In a lot of different problems, you'll see this come up, but just remember that any even number is not a prime number except if that number is two. So two actually. So for example, any even number will be always divisible by 2, right? So if that number is divisible by 2, that means that uh, it has 1, 2, and itself as all of its divisors, and so it's not a prime number. 2 is too small to be a uh, on basically what you call a number that's not a prime number is a composite number, right? So composite number is not prime. Composite numbers have composite numbers basically have more than two divisors. So for example, 4 is a composite number because it has three divisors, 1, 2, and 4. um, 2 obviously, as you can see, is too small to be a composite number because its only divisors are 1 in itself, and every other number is larger than 2 to be a divisor of 2. Do you get? So um, I guess that's it for prime numbers. So basically, the main takeaways from what a prime number is that a prime number has two divisors, one in itself. So a prime number always has two divisors, and anything that's not a prime number is a composite number. And then a divisor is a number that leaves no remainder when divided by the larger number. So for example, 3 and 6, if you divide 6 by 3, you get that the remainder is 0. So 3 is a divisor of 6, right? Um Now we'll move on to the fundamental theorem of arithmetic. So basically what this is that the fundamental theorem of arithmetic, you don't really need to know the terminology for this. It really is not that important. What's more important is knowing what it is and like applying it to problems, right? So basically for the this theorem states that this theorem is that um a number can be expressed, oh, my pen, wait, as multiplications, as a multiplication of various prime numbers up to the size of the number, right? So obviously, I'll go into that, and I should say always here. So basically, what this theorem means is that uh so first of all, why did I say up to the size of the number? Obviously, what I mean by that is that say you have a numbers, I don't know, let's say 8, right? Obviously you can express 8 as 2 times 4, but according to the fundamental theorem of arithmetic, you can simplify this factorization even more, because it says that a number always can be expressed as a multiplication of various prime numbers. Here 4 is not a prime number, right? So you can break this down even further. So you can break this, so 8 becomes the 2 times 4. Then you can break this 4 down into 2 and 2, right? Because these two, 2 times 2 is 4, and then 4 times 2 is 8. So you might have seen this in terms of what's called prime factorization. um, and so basically the fundamental theorem of arithmetic is basically why prime factorization works, is because a number can always be expressed as multiplication of different prime numbers up to the size of the number, because obviously you can't express um 8 as a, you can't bring in 11, right? Obviously not, because it's larger than 8. So you have to look at primes that are lower than the number. And basically if you not, obviously not all of the primes will work, because as you said, as you saw for 8, there's 2, 3, 5, and 7, but only 2 works. 3, 5, and 7 don't work. But what's important here is that one of those, or like one or multiple of those primes, have to multiply up to that number. But they can be, but they cannot be larger than the prime number or than the composite number, if that makes sense, right? So basically the rule that you have to kind of follow here is that a number can always be expressed as a multiplication of various prime numbers. So you could have, so for 8 you could have 2, 3, 5, and 7. Obviously 3, 5, and 7 don't work because, well, you just can't make 8 with 3, 5, or 7 without involving fractions in there, right? So um and as we said, a number that leaves no remainder when divided by the larger number is a divisor, right? So 2 is a divisor of 8. Is 3 a divisor of 8? No, right? Because if you divide 8 by 3, you get a remainder of 2, right? Because 6 and then 2. So the remainder is not 0. So as long as the remainder is not 0, you can't say that it's a divisor. And so I think that's it for the fundamental theorem of arithmetic. And basically, this theorem is basically why prime factorization works. Is that if you can basically you can bring the multiplication of that number, or the divisors multiplying up to that number, break it down until it reaches a prime number. So if you have 2 and 4, obviously 4 is not the last step, because 4 is not a prime number. 4 is a composite number. So you'd have to break that down into 2 and 2, and obviously you can't break it down even more because, well, 2 is a prime number and 2 is a prime number. So I hope that made sense. And I think I covered a bit of factors and multiples and back when I talked about divisors, but basically a factor and a divisor is more or less the same thing, right? So a factor, again, I should maybe say, so a factor or a divisor is a number that, when you divide it by the larger number, it leaves no remainder. It leaves zero. So it's perfectly divisible by the larger numbers. So you can talk about 2 and 8, you can talk about 4 and 8, but obviously 3 and 8 doesn't work because the remainder is not zero, if that makes sense. And then a multiple of a number is going to be, again, it's going to be the opposite of a divisor. So, okay. So a multiple of a number is going to be an opposite of a divisor in the sense that, if you have 2 and 8, right? Uh, so the A is a multiple of 2. So a multiple is always larger than the divisor, if that makes sense, right? So multiples of 2 could be 4, could be 6, it could be 8, it could be 12, and so on, right? So basically, factors and multiples are opposite to each other, where if 4 is a factor of 2, or if 2 is a factor of 4, then 4 is a multiple of 2, where where basically multiples. Right. So, that I think that's a good way of putting what multiples are, basically. So numbers that you can get by multiplying integers to the number in concern. So say the number in concern is 3, right? I can basically have multiply this number by any integer and get multiples of 3. So an integer obviously is not a fraction, it's not a square root, it's not a decimal, it's just an integer with no fractional or decimal parts, right? So 3, obviously 3 is a multiple of 3, because I can that then the integer would be 1. Then I can do 6, I can do 9, 12, and so on, right? So multiple of a number is basically numbers that you can get by multiplying integers to the number in concern. So if you wanted to get multiples of 4, you'd have to do 4 times 1, 4 times 2, and so on until you get like the multiple of 4 that you want. Right? So does anyone have any questions on either prime numbers or the fundamental theorem of arithmetic or factors slash multiples before I move on? All right. So now I'll be going over divisibility rules. You guys might have had some exposure to this, but there might be some that you don't know. So just it's always good to cover them. So obviously, a multiple of 2, you can see that if the last digit of a number is 0, 2, 4, 6, 8. So the last digit has to be 0, 2, 4, 6, 8. Then it's a multiple of 2, right? You can say the number is divisible by 2. So 42 would be a good example. 66 would be a good example. So the number always has to end with 0, 2, 4, 6, 8, like one of those. If you want something to be divisible by 3, you have to add up the digits. So sum of digits has to be a multiple of 3. right? So what I mean by that is you could have like the number say 123, right? So 123 is a factor of 3 because or a multiple of 3 because it's divisible by 3 because um if you add up all the digits 1 plus 2 plus 3 you do end up getting 6, which and 6 is a multiple of 3. So that's how you determine if a number is divisible by 3. If a number is divisible by 4, uh before I go over that, does anyone want to share? So if a number is divisible by 4, then the last two digits, so last two digits has to be a multiple of 4, right? So right, so that's why not every multiple of 2 is a multiple of 4, because now the last two digits have to be a multiple of 4. So for example, if I had the number 164, now the last two digits are are there a multiple of 4? Yeah, sure, because 4 times 16 gives you 64. So that number is a multiple of 4. But if I had 134, are the last two digits a multiple of 4? No, because 34 is 2 times 17. So obviously that's not a multiple of 4. So you can't say that this number is divisible by 4. So for numbers that are divisible by 4, the last two digits have to be a multiple of 4. Um, 5, I'll go over 5. So 5 is basically number has to end with 0 or 5. Last digit. That's it. It's much simpler than 4 or 3. It's just you look at the last number. If it's a 0 or 5, it's divisible by 5, such as 135. If it's not, then it's not. For a factor of 6, you'd have to look at two different things. So remember that for a multiple of 6, you'd have to look at two different things. Remember that two factors of 6 are the numbers 2 and 3. So the number that in concern, if it was to be a multiple of 6, would have to have both of those, right? So say you had an integer n, is the last digit 0, 2, 4, 6, or 8. So last digit has to be uh, even, right? Even, right? So 0, 2, 4, 6, and 8 are all even, right? So last digit has to be even, and then the sum of digits also has to be divisible by 3. So for example, um, a number like 96, say, would be an example of a number that's divisible by 6, because the last digit is even 6, and then the sum of the digits, which is 9 plus 6, that's divisible by 3 because the sum is 15, right? But something like, say, 39 wouldn't be divisible by 6 because it only meets one of the two criteria. It means that the sum of digits are divisible by 3, but 9 is the last digit, and 9 is not an even number, right? 7, I'm not really aware of a divisibility rule of 7, so maybe if Daniel is, he can share, but um, I'm not really aware of a divisibility rule of 7. Um, so going on to A, again, 8's one of those numbers where it's like if the last two digits, um, so I believe is the last three digits. So right, so last three digits have to be divisible by 8. Right. So obviously this is not really very useful for either two digit numbers or three digit numbers for that matter, because I could have a number like 168, right? and it's divisible by 4 because you can get 4 times, I believe, 42 is 168, right? But I wouldn't really know if it's divisible by 8 just by looking at the number, if it's a 3 digit or a 2 digit number. But obviously, it is divisible by 8, but I wouldn't know that just straight off looking at the number. But if it's a 3 digit number, then you can look at the last 3 digits, see if it's divisible by 8, and if it is, then that number is divisible by 8. So it's really useful for the numbers that have digits that are more than 4 or greater than or equal to 4. Right. So nine is basically a more specific case of 3. So whereas 3 was sum of digits divisible by 3, 9 is sum of digits have to be divisible by 9. Right? So something like 18 would be divisible by 9 because you can sum of the digits and you get 9. So 1 plus 8 is 9. But then something like 12 wouldn't be because if you sum 1 and 2, you get 3, right? So the sum of digits have to be divisible by 9 for the number to be divisible by 9. And then 10 is very easy. 10 is just if the number ends in 0. Number ends in 0, then it's divisible by 10. Otherwise, it's not. Right. And then the last divisibility rule, which is actually kind of kind of trickier than the other ones that I covered, is that of 11. And this is the divisibility rule that you guys might or might not know. Um, and the divisibility rule for 11 is that in a number, look at every other digit starting from the first, right? Actually, me writing this down probably um won't be as clear as if I showed you some examples. So let's say I have the number 121, right? So you always start with the first number, which is 1. You look at every other digit. So you skip the 2 and you look at the last one, right? And then you add these two numbers. So 1 plus 1 gives you 2. And then you look at, so basically if you start at the first digit and you skip over the number to the second digit for to the third digit or so on, you'll miss the numbers in between, right? So now you want to take care of the numbers in between. So in between I have 2 and nothing else. So 2, right? But in an idea, in if this was more than 3 digits, you'd be adding all those numbers that you missed, right? Just like you added the first numbers, and then you'd be subtracting these two numbers, right? So 2 minus 2 is 0, and if subtraction is divisible by, yeah, so subtraction divisible by 11, then the number is divisible by 11, right? So that's kind of harder to get your mind across. We'll go over one more example. So let's say I had the number 1661, right? So exactly what I mean. You start with the first number, and then you skip over 6, and then you look at the next number. So 6, and then you basically you skip all the numbers in between. So 1, 6, and then since there is nothing to the right of 1, that's it. So 1 plus 6, 7, right? If there was something to the right of 1, you'd go there, you'd skip over the 1, right? And then after that you take over the numbers that are left, right? So 6, and then you skip over this 6 because you already counted it. Then you go to this 1, and then there's nothing to the right of, so, so there's nothing else, so you just leave it at there. So again, 1 plus 6 is 7. And so is this number divisible by 11? Yeah, because if you subtract the 7 minus 7, you get 0. And so subtract if the subtraction is divisible by 11 or it is 0, then the number is divisible by 11. Right? So again, the rule for that is, so the rule for 11 is that if you have a number, say A, B, C, D, E, F, you'd add up, you'd start from A, you'd add up all the odd, if you'd like to think about it this way, this could help. It's like if you start with the first digit, then you look at all the odd placed digits, right? So A is the first digit, C is the third digit, E is the fifth digit, right? So these are all the odd placed digits. So A plus C plus E, and then you look at all the even placed digits. So B plus D plus F, right? So B plus D plus F, and you sum these separately, and then you subtract them. So A plus C plus C minus B plus D plus F. And if this subtraction is divisible by 11 or 0, then the number A B C D E F is divisible by 11. I hope that made sense. So obviously 11 might be something that you guys might not be familiar with, or you might. And then I think GCD slash LCM. Um, I think actually Daniel can cover GCD slash LCM. I'll just quickly go over perfect squares and then um, we'll move on. So perfect squares are basically numbers that so perfect squares are numbers that, like, you can multiply two of the same numbers to get. So okay, I'll show this through an example. So 36. Is 36 a perfect square? Yes, because the thing is, you can multiply two sixes and get 36, right? So the condition for a perfect square is you should get that number uh, by multiplying two of the same numbers less than itself. And I think this is a good way to put what perfect squares are. Basically, if you have, say, a number, I don't know, let's say you had 64, right? So you're gonna look at all the integers that are less, or numbers that are less than 64, and you try to get. So if you can make 64 by multiplying two of the same numbers, and obviously you can do that because 8 times 8 becomes 64, then that number is a perfect square. And I think perfect squares are very useful to spot in contests because it's a very useful um, like it simplifies a lot of different problems. If you can spot perfect squares, then a lot of problems become infinitely much easier than if you were just trying to deduce if they were perfect squares, or not really knowing what they mean, right? So I think perfect squares, knowing what they are and being able to identify perfect squares and the properties that come along with them is very important for uh, not just the AMCA, but a lot of different competitions in the future as well, including the SAT if you plan on taking that. Um, right. So this is basically what a perfect square is, and that sums up what I wanted to cover. Is there any questions on either divisibility rules, factors, multiples, perfect squares? Yep. Yeah. Feel free to ask any questions in the chat. If not, then I'll hand it over to Daniel now. Thank you, guys.
All right, cool. Well, thank you very much, Sid, for covering all the fundamentals of number theory. I'm gonna screen share my screen, and we'll continue by covering GCD and LCM. Is it working? Can you guys see my screen? All right, cool. All right, so let's continue with the concepts of number theory with GCD and LCM. GCD and LCM are abbreviations for two very important concepts that you'll often see in tackling problems involving multiples and divisors. So GCD, as we commonly refer to it as, stands for greatest common divisor. And in a likewise manner, LCM also has a abbreviation of least common multiple. All right, so you might be wondering, like, from these two definitions, right? We have a divisor or a multiple part of the abbreviations, right? Like greatest common divisor has a divisor part, least common multiple has a multiple part. But you might be wondering, like, there, what if we could have something like a little bit switched up? What if we could have something like greatest common multiple? Because with these definitions, it's really interesting that we have a greatest or a least part. So we want to find the maximal or the minimal of something, and that something is the divisor or the multiple. And so with that idea in mind, what if we have a, like, what would happen? Like, why are we not considering the other two possibilities that I'll be covering, like one of which will be greatest common multiple? Like, why don't we just have that, right? Well, let's consider two numbers, like two random numbers. Let me just pick 2 and 3. And let's just see what the greatest common multiples are, is of these two numbers. So if we list out the multiples, right, because we want to find the greatest common multiple, the greatest number that is a multiple of both 2 and 3. So if we list out the multiples of 2, which will go like 2, 4, 6, 8, 10, basically all the even numbers are divisible by 2. And if we list out the multiples of 3, like 3, 6, 9, 12, 15, 18, and I'll just add a couple more here with the multiples of 2. Let's see which numbers are present in both lists. Because if a number is in both lists, that means that that specific number, is divisible by 2 and 3. So with that in mind, let's just traverse the list. Let's just traverse the two lists and see if that number, the number we're currently pointing at, is also present in the divisor list, the multiple list, sorry, of 3. So let's do that. So let's first consider 2. Is 2 in the the list of multiples of 3? Well, the least number is 3, so we're not going to have that. So 2 is out, right? What about 4? 4 is also not in the list, in the second list, so it's out. 6 is, however, in the list, so 6 is a potential candidate because it is a multiple of both 2 and 3, but we're not sure if it's the greatest common multiple. What about 8? Is 8 in the second list? No, it's not. So that's out. Is 10? No. 12 is. So instead of 6, we cannot have 6 as the greatest common multiple, because the greatest common multiple must be the maximal, because we already found a number that is present in both lists. So we can't have 6. 12 so 12 works. 14 doesn't work. 16 doesn't work. And if we list out one more number, we also see that 18 works. So 18 could be the greatest common multiple of 2 and 3, and 12 is automatically out because 12 is less than 18. And we could continue this process of finding a number present in both lists as we keep increasing numbers in the multiple list of 2 and 3. So that's interesting because we can see that 6, 12, and 18 all differ mutually by 2. By 6. Because 6 and 12 have a difference of 6, and 12 and 18 have a difference of 6. And then we can just keep adding 6. So we can predict the next number. The next candidate will be 24 and 18 will be out, and so on. And so you can see that by this whole process, we're not going to get a definite number for the greatest common multiple, because the greatest common multiple eventually is going to keep getting bigger and bigger and bigger, and we're never going to get to a definitive value for the greatest common multiple. And so that's why we don't have greatest common multiple. That's not really such a thing. We're just gonna the multiples are gonna keep increasing. We're gonna have to find a new number in both multiple lists. So that's an explanation why we don't really consider the greatest common multiple, because there really isn't a greatest common multiple that we because it's just infinity. It's gonna keep getting bigger and bigger. All right. So the other question that's really important to answer is, let's throw it right there, is like what about the concept of least common divisor? What about that, right? Like what is the minimal number that is a divisor of 2 or more numbers? So let's consider that question, and let's do it with the same numbers. Let's do it with different numbers, slightly different numbers. Let's try with 6 and 8. So with 6 and 8, what are the divisors of 6 and 8? So let's list out the divisors of 6. So remember that when we want to extract the divisors of a number, we only need to consider the numbers that are below that number. Because if you have 6 and you consider a number like 12, right? 12 is 6 is never divisible by 12, because 12 is a bigger number than 6. So like another way that you can think about it is that 6 divided by 12 it's not an integer. This is actually just a fraction. And so divisors will always result in a division of an integer when it's divided by the bigger number. So 6 divided by 12 is gonna not be an integer, and so we can't have 12 or any bigger number than 6 as a divisor. So let's consider the numbers from 1 to 6. The first number that we want to consider is 1. So well, before I have a tendency to spoil this, but we know that 6 is divisible by 1, because 6 divided by 1 is an integer. So 6 divided by 1, we just know that it's going to be 6. So let's consider 2. So the next number is going to be 2. Is 6 divided by 2 an integer? Yes, it is. It's just 3. What about 3? 6 divided by 3 is 2. Okay, what about 4? 6 divided by 4 is, well, that's not a EVC like division rule that we know, so we can't have 4 as a divisor of 6. So there's no integer when multiplied by 4 that will give us 6. And so what about 5? 5 is our next one. 6 divided by 5. Well, no, we can't have 5 with the same logic. And 6 is obviously divisible by itself. 6 divided by 6 is just 1. All right. And I'm not going to repeat the process for 8, but you can imagine that if you do the same reasoning, you will get 1, 2, 4, 8 as the divisors of 8. All right. So what is the least? So remember that the problem that we were trying to answer, right? The least common divisor. Because remember that we had greatest common divisor, least common multiple, and greatest common multiple, which we discovered that really wasn't a thing because the multiples will keep increasing and increasing. You won't ever get to the greatest because it's just going to go to infinity. So now we're answering the question, what is the least common divisor of 6 and 8? Well, what are the numbers that are common to both lists, the divisor lists of 6 and 8? Well, let's circle it in red here. We have 1 because 1 is present in both lists, and we also have 2 right here. So what is the least common divisor of 6 and 8? Well, it's just going to be 1. And since like 1 is such a nice number, you can infer that no matter like how many numbers you repeat this process with, you're always going to have a divisor of 1 for each number. And so since you also might be maybe asking like what if there's like a -1, because like 6 divided by -1, if you learned about negative numbers, it's just -6, and that's an integer. Well, so with number theory, we typically with like multiples and divisors, we typically think about positive integers. So that's why the least possible divisor for a number is 1. And so since every number is divisible by 1, we're going to say that the least common divisor of any set of numbers is going to be 1. So that's why the least common divisor of any two numbers is just 1. So all right, so let's go back to the original definitions of the greatest common divisor and least common multiple. So what actually are these two, and why are they important in solving problems? So let's actually repeat the process that we did. Let's cover greatest common divisor first. Let's repeat the process that we did by finding the least common divisor, except this time we're trying to find the greatest common divisor. So basically it's asking like if you were to list out all of the numbers that are divisible by if you're listing out all the divisors of the two numbers that you're interested in, what is the greatest number that will pop up in both of the lists, right? So with greatest common divisor, we typically denote this concept as GCD of AB, where A and B are the two numbers that we're interested in. We can also have GCD of A, B, C, or just however many numbers that we want. And so let's consider the two number case, right? If we want to find the greatest common divisor of 6 and 8, you may also see the notation GCF, which is the greatest common factor, which is just the same thing. Let's just do this with the factor list technique, and we'll see how we can use this with other tricks later on. So I'm gonna copy and paste this list. All right, there we go. So we have the divisor list of 6 and 8 already, which is really nice. And we want to find the greatest number that is common to both lists, so that appears in both lists. Well, that's like really easy because you can just eyeball it here. 2 is the greatest number that is common in both lists. And remember that these are divisors abbreviated div, the divisor list of 6. So they're all divisible. 6 is divisible by all of these numbers. And so we know that GCD of 6 and 8 is 2 for that reason. All right. So before we go on to more advanced techniques of finding the greatest common divisor and least common multiple, let's just cover the least common multiple of 6 and 8. So the least common multiple is kind of like the process that we did with greatest common multiple reversed. So let's copy and paste the whole thing. I'm gonna make this like a lot smaller. All right. And I'm gonna rewrite I'm actually just gonna rewrite the whole thing because I think that's just gonna be a little bit easier. All right, so let's find not the greatest, but the least common multiple. The least common multiple. The least common multiple of 6 and 8. All right. All right, so let's list out the factors. So these will be the factors. Sorry, no. The multiples. The multiples of 6 and 8, because we want to find the greatest least common multiple. So we want to list out the multiples of the two numbers. And when we find the least common, I said, when we want to find the greatest common divisor, we want to list out the divisor of 6 and 8. So let's start by listing out all the multiples of 6 and 8. So with 6, we're gonna start from 6 because we like 0 is a multiple of 6, but remember what I said earlier about like dealing with integers in number theory. We typically want to think about positive integers. Sometimes negative integer will come in like certain contexts, but like for our purposes of multiples and divisors, we want to deal with positive integers. So our least multiple of 6 is just 6 itself. And we're just going to keep adding 6 to the previous term to get our next term. So adding 6 to 6 will give us 12. And adding 6 again, 18, 24, 30, etc. And then with 8, we're going to start with 8. And then just keep adding 8. So that's 16, 24, 32, 40. All right, so I just listed out the first 5 terms in each of these lists. All right, so how do we find the least common multiple? Well, it's going to be really self-explanatory with these multiple lists because all you need to do is to find the smallest number that is common to both lists, just as we did with divisors. And so let's just scan this list, iterating over the multiples of 6. We can start with 6. Is 6 present in both lists? No. Is 12 present in the second list? Nope. Is 18? Nope. Is 24? Yes, because we got two 24s right over here. And there you go. That's it. We abbreviate LCM, very self-explanatory. LCM is the least common multiple. And so the LCM of 6, that's a weird 6. 6 and 8 is 24. And that's our least common multiple. All right. So I'm going to close off with a few strategies that can facilitate the process of finding either the greatest common divisor or the least common multiple. And so the reason we kind of want to find these more efficient methods is that, like, if you want to find, let's say you want to find the the greatest common divisor of like, I don't know, like 92 and 52, you wouldn't really want to like start by listing out the divisors of both 92 and 52, although it could work, because sometimes when the numbers get really big and nasty, you're gonna have to use like all of your divisibility rules and also check for like bigger primes. That can take a really long time, and so um, and actually, I think that is kind of like part of the method that I'm going to show you guys. But the real main reason is to like not do the divisor listing, because that might take a while, and the divisor listing itself is it can actually be um, be made easier by what I'm about to show you. So if we consider, let's actually just try. Let me think. Let's just try the easy example again, 6 and 8, just so you can see the process. All right, so 6 and 8. There are a couple of ways that you might have learned in school that you might have that I might be like showing you. Uh, so this way will be called um, the boot method. All right. So this is kind of like the basic idea is to use division to whittle these two numbers down until they don't have a common divisor, which may sound like a little bit like circular in reasoning, because like you're trying to find like the greatest common divisor. So again, this is the problem with GCD. It's find the greatest common divisor. These you're finding divisors, and then but you'll see what I mean by like whittling down these numbers. So our main goal is to reduce these numbers such that they don't have a common divisor at all. So what I mean is that like 3 and 5 can be a result, because 3 and 5 don't share a common divisor. You can also have 4 and 7. You can have 1 and anything really. You can have 1 and 9. So that's kind of what I mean by whittle down these numbers. So let's do that with 6 and 8. What's a common divisor of 6 and 8? Well, they're both even. One of the first things that you should check when computing a greatest common divisor is checking if both numbers are even. Because if both numbers are even, that means that they will be divisible by 2. And so let's divide both of these numbers by 2. That's kind of like what this boot symbolizes, dividing by something. And so let's divide 6 and 8 by 2, each by 2. We'll get 3 and 4. Do 3 and 4 share any common divisors? Oh, no, they don't. We could test it like one. Well, they do uh, share a common divisor of 1, but the main like this state will be okay, because what I meant by whittling down these numbers such that they don't share a common divisor is that they shouldn't share a common divisor. They shouldn't share a common divisor other than 1, because 1 is obviously a divisor of any positive integer, and so 3 and 4 they don't share any common divisors other than 1, and so we're done. And so the GCD will be just 2. But what about something like something a little bit more involved? Let's say like you got 12 and 18. So let's do that. Well, are they both even? Um, so GCD of 12 and 18. So we're going to compute that. So are they even? Yeah, yes, they are, because, well, 12 and 18, they're even numbers. So 12 divided by 2 is 6. 18 divided by 2 is 9. All right, cool. So 6 and 9, are they even? Are they both even? No, because 9 is odd. So then we have to try other numbers. So let's try like 3, because that's like naturally, like that's the number immediately above 2. that we haven't really tried. So dividing 6 and 9 by 3 will give us 2 and 3. And so do 2 and 3 are 2 and 3 both even? No. We could test out other divisors like 3, 4, and other numbers, but note that like our smallest number is 2, and so we only need to consider just 2, and 3 is not divisible by 2. So this is our final result for the two numbers. So we've whittled down 12 and 18 all the way to 2 and 3. And along the way, we have 2 and 2. We divided, we divide by 2 and 3. So what's our greatest common divisor? Because we have two numbers, we divide by 2 and 3. So how do we get the common divisors? So remember that when we divided by a number, when we're dividing by a number, we're kind of incorporating that number as a divisor. So if we can divide successfully 2 and 8 by 2, then that means that 2 is a divisor of 2 and 18. And that must be the greatest common divisor of, 12 and 18. And so we can just multiply all of these numbers that we just divided by. So these numbers. And so our answer is just going to be 2 times 3, and that is just 6. That's our greatest common divisor. All right, so cool. What about the least common multiple? So let's do our simple example of 6 and 8. So let's compute the LCM of 6 and 8. So what's that? Well, we can actually do this with the boot method, and I'll show you how. We want to whittle down these numbers. So we divide by 2 because both are even. That'll give us 3 and 4. And then 3 and 4, that's our final state. And so to find the least common multiple, we kind of want to like draw a boot. This is kind of like why it's called the boot method. We want to draw a boot that incorporates all of the numbers that we divided by and the final two numbers. And maybe in future lessons we'll explain like why this works. And for now, you just need to know that this is kind of like the general process. And so our final answer is just going to be the product of all the numbers in the boot. That will be 2 times 3 times 4. That'll give us 24. And so let's do that. Again, we can do it for 12 and 18. 12 and 18. I'll just copy down the process we did here. So again, like if I were in the AMC8, I would be going like kind of fast with this. So both are even, divide by 2, you get 6. 12 divided by 2 is 6. 18 divided by 2 is 9. Are they both even? No. So try 3, that's the number above it. And 6 divided by 3 is 2. 9 divided by 3 is 3. Or 2, let's try out like divisor of 2 because that's the smallest number. Or 1 and then 2. So this is the final state. And so we draw our boot, and multiply all the numbers in that boot to get the LCM of 12 and 18 is 2 times 3 times 2 times 3, which is 36. There are obviously other ways to do the LCM besides the boot and factor listing, but we are running out of time. So hopefully next time or in a future lesson, we'll be covering factor trees, which is really useful for finding both the GCF and LCM. And sometimes it can be less confusing than dividing like these numbers up because they will require the use of the divisibility tricks. All right, cool. So thank you so much for attending. We'll be sending out a recap email of the recording and the handout.
Yeah.
And next week we'll be covering more number theory. So we'll see you then. Thanks
All
for
right.
coming.
Thank you guys. Bye.
Bye everyone.